Hi and welcome. I am Audrey Malagon, the new Senior Director for Programs at the Mathematical Association of America, and I am thrilled to welcome you all to tonight's Distinguished Lecture Series. As you are joining us, if you would just drop in the chat where you're joining from, we'd love to see how many of our members and mathematicians and math enthusiasts show up from around the country to hear these talks on different topics. We also wanted to let you know that MAA Open Math is back this summer. This is a National Science Foundation funded project that offers online teaching-focused professional development for faculty. We have 7 exciting workshops this summer. So in the chat, you will see a link to MAA Open Math. You can check out the workshops in the descriptions there. So thank you again for joining us. I'm going to turn it over to Executive Director Michael Pearson, who's going to tell us a little bit more about tonight's lecture.
Yeah, thank you, Audrey. Well, I'm certainly very excited to be here. I think this is going to be fun for me. It's kind of a little selfish project of my own. I was talking to some friends of mine year or so ago, and we just got to talking about the dipole, the magnetic field of the Earth, and some other things. And so that conversation, they recommended me to get in touch with some people, one of whom was Bruce. And so, Bruce, it's so great for you to be here tonight. I'm really looking forward to hearing this. You know, it was about 160 years ago now that William Thomson, Lord Kelvin, used the thermodynamics to estimate the age of the Earth. And he, thinking about it as if it had started as just a molten thing. But he didn't know the things we know today, like radioactive decay, for example, generates some additional heat. So his estimate was off by quite a bit. But the idea of using data and mathematics to understand the planet is something that has been carried on ever since, and is very well reflected in your work to understand the dynamics of the Earth's core, the interactions between the mantle and the core, and the way that and the effects that has on the magnetic field of the Earth, which for those of you who don't think about such things very often, without that magnetic field, the Earth would be stripped of our atmosphere by the the particles that are hitting us constantly every day, day in and day out. And so that magnetic field we rely on for our life to be able to live here. And Bruce, you've been studying these things for quite a while. The question of subduction, the interactions between the mantle and the core, and the idea that where the tectonic plates collide with each other, what happens? Well, there's a lot of dynamics there. And so the way that you have, and then as I understand it, there's new ways to collect data using satellite measurements and so forth. So as we are able to get more and more data, we're able to bring more and more insight into the mathematical models. And that's what Bruce is going to talk about tonight. So I'm excited about that. Now, Bruce is a theoretical geophysicist who's currently at University of California, Berkeley. Been there for quite a while. He's in the Earth and Planetary Science Project, and also part of the Center for Integrative Planetary Science there. And Bruce, you were elected as a fellow of the American Academy of Arts and Sciences in 2018. And as I said, you've been working on these questions for many years. I think some of your work on induction that I was talking about was around 2010, or in the years leading up to that. So I'm just really excited to hear about how mathematics and planetary science helps us understand the world we live in and all those things. So thank you for being here, and please take it away.
Well, thanks, Michael, very much, both for the introduction and for the invitation to be here. I'm actually delighted to be here. And I think your description of the general problems and approaches is really on track for the things that I'm going to be talking about tonight. If you were to go to the web and download an image of the Earth's magnetic field, you would probably end up getting something that looks a little bit like what I've got on my screen right now. It would show a mainly dipole magnetic field. The axis of that dipole would be largely, not perfectly, but loosely aligned with the rotation axis. And so it's actually a pretty reasonable description of what we see on the surface. The details of what go on in the interior, much well below the surface, are much more complicated than this. And we rely on both mathematics and physical models, and to some extent observations, to try to really get a handle on what's going on. And this is really what I wanted to focus this talk on, is the mathematical tools that we use to make insights into these questions. There's also a planetary connection in this, and we often think of planets in general as often having magnetic fields, and many planets in the solar system do, but it's interesting that our two nearest neighbors, Mars on the left and Venus on the right, do not have magnetic fields. And it's a little bit surprising because we really don't expect there to be very much difference in their internal structure. Mars, Venus, and Earth all are expected to have a rocky mantle, here shown with that orange layer is sort of a rocky layer called the mantle. And the lower half of the planet by radius is mostly metal. It's mostly iron with some alloying elements in it. The outer 2/3 is liquid with a viscosity that's probably comparable to water. And then the innermost 1/3 is solidified. And the fact that it's solidifying at the center where it's the hottest is just simply a consequence of the pressure dependence of the melting temperature. So I have sort of personal thoughts, I think, about why Mars and Earth and Venus are all different. And I think it actually relates to the dynamics of the orange region, the mantles. But in this talk, what I really want to do is zoom in on the dynamics that's going in the liquid metal part and really to understand what's going on in that part of the planet. And so the science question really is, how can flow in a rotating, conducting fluid produce a magnetic field that we see on the present day Earth? And in these images, what I'm showing you is just in the first image on the fluid flow, I'm just simply showing the core part of the model. You can sort of see columnar structures, which we're going to talk about a little bit. And then on the right-hand side, you see an image that covers the entire Earth. So the inner half will be where the core is, and you can sort of see that the magnetic field is very complicated and distorted in that region. And then by the time we get to the surface, which is sort of the outer regions of those magnetic field lines, we've got something that looks pretty much like a dipole. And so this is the question that we want to pose. How does this work in principle? So we'll start with a description of the problem. There are three essential ingredients. And the first one is the momentum equation, really just the statement of Newton's second law, here in the form MA equals F. And we typically write this equation in the rotating frames. So we have local inertia here. We also have the Coriolis force. And the centrifugal effects, we typically move on to the other side and include in a description of the local gravity field. The forces can depend on the velocity, V. For example, viscosity and frictional forces will enter there. We can have temperature anomalies, which produce buoyancy, which drive flow, and so the forces can depend on temperature. And there's also going to be Lorentz forces, where the magnetic field itself exerts a back reaction on the flow and affects the evolution. And so there are a number of sort of unusual or unique things about the nature of this particular problem that you can identify by thinking about the relative importance of some of the terms that appear in this equation. And so the first one that I'm going to focus on is the ratio of the local inertia, sort of these terms essentially here, divided by the Coriolis force. So this is in the denominator, the rotation rate of the planet and some characteristic length scale, which we might take to be the radius of the core or maybe the thickness of the liquid shell. And for typical parameters that we think are appropriate for the Earth, that ratio is 10 to the minus 7. So it's small. This parameter has a name. It's often called the Rossby number. And the fact that that number is so small is telling us that rotation is going to have a very important role on the nature of the flow that we get in the core. The other ratio that I want to focus on is the ratio of the viscous forces to the Coriolis force. And this depends on the kinematic viscosity in the numerator, again, the rotation rate, and the length scale, in this particular case squared. And that number is an even smaller number. This is 10 to the minus 16. And we typically refer to this term as the Ekman number. And so both inertia and viscosity are going to be have a very, very small role in the momentum balance or Newton's second motion. It turns out that the ratio of these two numbers defines something that's known as the Reynolds number, which you probably have heard about. And you usually think about large Reynolds number flows as being very turbulent. And this is definitely a large Reynolds number, 10 to the 7 over 10 to the 16. So the Reynolds number is about 10 to the 9. On the other hand, it's a little misleading to say that as a consequence, the flow would be turbulent in the classical sense. Just the fact that the Reynolds number is big just means that the ratio of these two very small terms that have small role in the momentum balance are very unequal in size. And so we'll see some of the consequences of this come up a little bit later. So here are just some examples of numerical calculations that show the fluid velocity. And this first, on the left-hand side, I show a calculation by Nathaniel Schaefer and colleagues where the viscosity, the Ekman number, is 10 to the minus 6. So it's still got another 10 orders of magnitude to go. But what you can see is sort of the fluid region of the core. The central piece that you see at the center that's the solid inner core. And so the fluid is convecting with above the inner core and below the outer boundary here. And what you can see is that the velocities tend to be fairly independent of the rotation vector. They tend to sort of be extended in the direction with very, very weak variations in that direction. And that's a consequence of the strong influences of the rotation, the Coriolis force. In the equatorial plane, you can see a lot of small scale structure, but when you look at those equatorial planes, what you want to be thinking about is the fact that those flow structures extend almost invariantly above and below the equatorial plane. So here's another calculation that's just showing the equatorial plane only, and this one is done at an Ekman number of 10 to the minus 5, so a little bit bigger, further away from being Earth-like. And you can see that the structures are a little bit larger scale. If we show another calculation, this is a much more beefy calculation. This was run on a computer with about 100,000 cores. We could get the Ekman number down to 10 to the minus 7. And the thing that you'll notice as we're making the Ekman number smaller and moving toward more Earth-like parameters is that the length scale of the convection gets much, much smaller. And so from this 10 to the minus 7, we still have another 9 orders of magnitude to go before we get to Earth-like conditions. So that's something to bear in mind. The second component of the problem are Maxwell's equations. And for the problem that we're thinking about, where the fluid velocities are slow relative to the speed of light, we can use the so-called Magnetohydrodynamic approximation, the MHD approximation, and take all of Maxwell's equations and boil them down to a single equation that describes the time evolution of the magnetic field in response to the interplay between the convective fluid motions and the magnetic field, and then this diffusive piece, which represents the influences of ohmic decay or electrical resistance. So if the fluid was a perfect conductor, superconductor, this diffusivity eta would essentially be 0. For more realistic parameters, for sort of iron, this number is about 1 in SI units. And so the ratio of the induction term to the diffusion term is proportional to the velocity, a typical length scale divided by that diffusivity. And this is about 10 to the 3. And this is often referred to as the magnetic Reynolds number. And this is really the good news part of the story, is that this value of parameters is pretty reasonable. If we could get access to the fluid velocities accurately by some means, then we could solve the induction equation reliably for the magnetic field. And so the trick in this is going to be coming up with good estimates for that velocity field. If we were to take the velocity field and just simply set it equal to 0, then this induction equation reduces to a diffusion equation. And in fact, for typical values of that diffusivity, electrical resistance of the fluid, the decay time would be about 40,000 years. And so what this means is, at least on geological time, the core can never rest. It has to continually generate and regenerate the magnetic field, because in a relatively short geological time, the field would disappear without continual regeneration. Okay, the last piece of this is the heat equation, the one that describes the temperature anomalies, which are going to provide the buoyancy that drives the flow ultimately. And I've nominally attributed this to Fourier. Again, we have sort of the advective piece here and the diffusive piece, with the diffusivity being kappa. And we can think about the ratio of those two terms, the advective piece and the diffusive piece, and that's roughly on the order of 10 to the 8th or so. So it's, again, a pretty large number. And so this number would permit temperature anomalies in the convective system to persist down to probably meter scale, perhaps a little bit smaller. And those meter scale temperature anomalies are going to drive flows on the meter scale. And so the difficulty in resolving these very small scales is really an enormous numerical challenge. So here's just one example of those solutions. This is a numerical model where we put all three of those things together. And what we're looking at is the radiomagnetic field at the top of the core. And you can see that the northern hemisphere of this model is mostly blue, and the southern hemisphere is mostly red. So this is a dipole. But you see a lot more spatial structure at the top of the core, sort of surface where the field is being generated. And so if you were to look at this at the surface of the Earth, a lot of these fine scale structures, you would lose resolution of. You wouldn't be able to see them very effectively, and the field would mostly look like the much smoother background dipole field. Okay. So let's think about what we can use as observations to sort of test and refine and improve some of these models. As Michael was mentioning, for the last 20 years or so, we've had satellite observations. And so this has been profoundly important in terms of recovering estimates of the magnetic field. We're discovering that there's much higher frequency fluctuations of things going on in the core that we had no idea about. And the satellites are really illuminating this part of the problem for us. Going back to the time of Gauss in about 1840, he figured out how to make a measurement of the absolute intensity of the magnetic field, and was instrumental actually in creating observatories, which have gradually grown and are now around the planet. And we have about 180 years of observatory data. And then we also have these unique measurements that come from mariners that were exploring the New World. We were making measurements of magnetic field directions with compasses, both compasses that are mounted about a vertical axis, as well as compasses that are mounted about a horizontal axis. And they were able to make measurements of the orientation of the magnetic field in space, going back really to 1590. And so if we take those observations, we're able to construct models for the magnetic field at the surface of the Earth, going back to 1590. And what I would like to do is just show an animation that shows the evolution of the magnetic field from 1590 till 1990. And what you'll be struck by, I think, or I hope, is just how variable the magnetic field is on these historical timescales. Something happening there in the southern hemisphere. That's the South Atlantic anomaly, which is sort of interesting for a variety of other reasons, but we'll probably not go there. The point is that the field is varying quite a bit on these historical timescales. And in fact, we think most of the changes in the magnetic field are a result of fluid motions at the top of the core. If we were to take this magnetic field as we see it at the surface and downward continue it, assuming that the mantle, the rocky region, is a perfect insulator, which is not an unreasonable approximation, we can actually reconstruct. We'll just go. So this is what the field looks like at the core mantle boundary, and you're now getting closer to the source. It looks a little bit more complicated, a little bit more like that numerical model, but you can see that it's still predominantly dipolar. It's still mostly blue on the top, and it's mostly red on the bottom. But what we can do over time is we can see these patches of magnetic field being drifted around to different locations, and we can interpret their motion entirely in terms of fluid motions. And so this gives us estimates of the fluid flow in the core. It's several tens of kilometers per year. And the time scale required for fluid motions to go from the bottom of the core to the top, the so-called overturn time, is about 100 years. Okay. It turns out that there's actually a lot of similarity between the types of motions that you get in the core and the types of motions that you get in the atmosphere. In both cases, rotation plays a very, very important role, although the Rossby numbers, the importance of inertia in these two flows, is quite different. And we can use those comparisons to make this correspondence of timescales that says, roughly speaking, 1 day in the atmosphere is equivalent to about 60 years in the core. So we have roughly 400 years of these magnetic field observations going back to the earliest times of these explorers. And so that would turn out to be about a week worth of fairly sparse, the equivalent of a week of fairly sparse meteorological observations. So if you were thinking about the problem of the weather, predicting weather, 5 days of observations might be useful. But if you're thinking about the problem of climate, then we would really like to have more than just 5 days of observations to understand how the climate system works. And I think the same thing applies to the core. To really understand the climate of the core, to understand things like magnetic reversals and other phenomena that we know have existed in the past, we need to figure out ways of extending the observational record further back in time. So this is inevitably going to require us to make use of the geological record. So igneous rocks, which are formed when lavas cool at the surface, can actually record both the direction and the intensity of the magnetic field in the past. So these lavas erupt, they cool and solidify on the surface, and as long as their temperature is still above the Curie temperature, for a lot of natural magnetic minerals is about 500 or 600 degrees, there will be no magnetization of those minerals. But once you drop below this transition temperature, the magnetic minerals, things like magnetite in the lavas, will become aligned with the magnetic field and then get frozen in. So I can now subsequently take the imposed magnetic field away associated with the Earth, and the magnetization of those original grains is preserved. So the field could reverse. I could go analyze these samples, and I would know both the strength of the magnetic field and its orientation in the past. And so these are the observations that tell us that the Earth's magnetic field has reversed sporadically in time. This is a sort of a chronology of when the various reversals, the black are the normal for the current time, and the white is for the reversed state. And you can see the last time the field reversed was 0.78 million years ago, so 780,000 years ago. But you can see there have been other times in the geological past where these intervals were either much shorter or potentially very much shorter. And so the geological observations are the thing that is providing us insight into this process taking place. The other source of information we have, remarkably enough, comes from the collection of sediments. As sediments fall to the deep ocean and they gradually settle, magnetic minerals will tend to sort of be aligned with the direction of the magnetic field. And the stronger the field is, the more of those grains will be aligned, and we can actually go back to these sediments and actually get estimates of the direction of the magnetic field and something about the relative intensity of the magnetic field. It's really difficult to get quantitative estimates, but what we can say is that if sediments are more magnetized than other times, then probably when those sediments were forming, the magnetic field that was present was a little bit stronger. And so this is an example of the kinds of things that you can do with sediments. This is a stratigraphic position, so we've drilled a hole into the ocean. We're recovering sediment cores and making measurements of the magnetization of those sediments. And we can see one polarity at a certain depth. We then have this transition region, which takes place probably over about 10,000 years, and we gradually move into the opposite polarity. So sediments are great because they provide a continuous record, but they don't provide us with a direct and interpretable estimate for the intensity of the field. And so what has been typically done in the models that we'll try to use and interpret using sort of mathematical techniques will be these so-called paleomagnetic time series. So these are largely based on sediments, and that they're calibrated at different points using the absolute intensities that come from the lavas. And so this is an example of one of those models. We're looking at an estimate for the axial dipole moment of the field as a function of time. And so time here is running from the right to the left. So we're starting at 2 million years and we're running to the present. And you can see large fluctuations in the magnetic field. You also might notice that at the time of the last reversal, at about 0.78 million years, the field was actually quite weak. And this is something that we think happens during a reversal, that the field will collapse, A lot of the charged particles that Michael was mentioning at the beginning of the talk will sort of bombard the surface, and then as the field essentially reestablishes the new polarity, the field will actually grow back out. So the question that I would like to pose is, how should we go about analyzing this record? What should be the tools that we try to use to extract insight from this? And the approach that we've been taking with this is to try to represent this process using stochastic differential equations. And in fact, there's a very, I think, nice analog between the problem of Brownian motion, which was the phenomena that spurred the development of stochastic differential equations, and the application that we have in mind. So if you think about Brownian motion, that involves the motion of a pollen molecule or pollen particle in a glass of water, and it's being bombarded by the impacts of the water molecules in the glass. These are happening randomly. You can't make out or see the water molecules, but you can see their consequence on the motion of the pollen molecule. And so we have something similar going on here. We have this large-scale axial magnetic field, which we can determine in the geological record, but we have no way of seeing and knowing the details of the turbulent flow that are actually producing this phenomena. And so the idea is to try to use a stochastic differential equation to draw insights out of this data record. So what I want to do now is just develop the physical model for the description of the axial dipole, and then how we represent this with a stochastic differential equation. Okay, so the magnetic moment, if I were to take a coil of wire with some current I and loop it in a big loop and power it up and send the current through it, the magnetic moment that I would produce would simply be the product of the current in amps and the surface area of that coil in meters. So we measure dipole moments in amps per meter squared. Now, we don't have wires inside the core. Instead, we have a current density that's amps per meter squared flowing through, and it's just distributed through the entire volume of the core, but we can still define a dipole moment by essentially integrating the circulation of those currents through the entire volume of the fluid core. And you can use the Biot-Savart law to convert this integral in the absence of external sources to represent the magnetic moment simply in terms of an integral of the magnetic field over the volume of the core. And to me, this is really very insightful, because if you wanted to have a magnetic moment which is mostly aligned with the rotation axis of the planet, then the way that we want to do this is by getting magnetic field primarily aligned in the direction of the polar axis. And so the question is, how do we accomplish this? It turns out in this integral, if we were to represent the magnetic field, let's say in a spherical harmonic expansion, which is very often the basis set of functions that we use to do this, it turns out only the dipole part of the magnetic field actually contributes to this, and sort of the degree 1 component of the spherical harmonic expansion. And so I'll just put an overbar above that to remind ourselves that this is only one part of the magnetic field, but it's the part that contributes to the moment which we can see in the geological observations and we can see at the surface. So this leads us to a description of how the dipole moment evolves as a function of time. I can just simply take the time derivative inside the volume because the volume's not changing. I have my induction equation from Maxwell, but again, just the projection of that onto the dipole part. And now I have a description of how I think the dipole moment is going to change. The types of flows that we think are important are sort of these columnar flows. Columnar structures are the kind of thing that gets produced when you have strong rotational effects. You can see sort of clockwise and anti-clockwise circulation in these tubes. There's also fluid motion going up and down. So I will often refer to these kinds of flows as helical flows. They have vorticity, which means that there's circulation around, and that there's motion up and down around that circulation, which gives rise to this helical kind of structure. And we think that those types of flows are really important for generating magnetic fields. But it's going to be impossible for us to sort of reconstruct in detail what the fluid velocities were actually doing. And so what we're going to do in the spirit of the Brownian motion problem is that we're going to try to represent that generation process with a statistical description of the source. And so this source, S, which is a function of time, but it can also be dependent on the strength of the dipole moment, we're going to try to come up with a statistical description of this. And then the dipole part, which is the second term, we're going to represent in terms of the dipole decay time. Okay, so this is going to be the basis for our model moving forward. Now, the convective processes in the core, I mentioned, those are with an overturn time of about 100 years or so. So the timescales for the fluid motions are, relatively speaking, short compared with the dipole decay time, which is on the order of 40,000 years. So what we're going to do is we're going to represent the source time by a series of impulsive functions in time. I'm going to thinking of these as being these helical convection events that have relatively short duration and some particular amplitude that we want to try to characterize. And in principle, you can replace the delta functions with some finite duration phenomena. But it turns out, actually, if you're thinking about the evolution on long time scales, actually the detail of how these events play out in time is relatively unimportant. I'm going to let the amplitude of this helical convective event be dependent on three things. I want it to be dependent on the amplitude of the convective motions, that's the A. It's going to be dependent on the current state of the magnetic field, and part of the reason for that is if the magnetic field reverses, if the dipole moment changes sign, then I would like the sign of my source term to also vary. And the last term is that we know when the field gets strong, it tends to suppress the role of convection. And so this F is often referred to as a quenching term that tends to suppress the amplitude of the motions when the field gets very large. Okay, so for the description of the timing of these helical convection events, I'm going to let that be a Poisson process. And I'm going to let the time interval between each of these convective events be described by an exponential distribution. And I'm going to let the amplitude of the convective events be simply described by a uniform distribution with some upper bound for the amplitude, or some lower bound for the amplitude rather, and some upper bound for the amplitude. So the amplitude in principle, a minimum, could be negative so that we could have convective events which are actually destructive. But if we want to generate a magnetic field on a time average, then we would need the average to actually be positive. And I think we're going to see in just a couple of slides that actually the specific choice that you make for the probability distribution of the amplitudes is not particularly important. What really matters is the first few moments of this distribution. Okay, so here's just an illustration of what you get when you apply this model. It's interesting. You get reversals. You see the field is fluctuating around 5 or something on 10 to the 22 amps per meter squared, and then occasionally it will reverse polarity, fluctuate around, come back. Some of these reversals are quite long, other of these are quite short. And so this is producing a record which looks very much, in many ways, like the geological record that we have to study. And so what we have to choose to constrain this model is we have to choose how often are these convective events taking place. And then we also have to set the limits, our lower limit and our upper limit, to the convective anomalies. And so for starters, let's just imagine that I'm taking this recurrence time to be roughly comparable to the overturn time, maybe 100 years. And I'm going to set the upper and lower limits on the amplitudes of these convective anomalies to match the mean and the variance of our geological record. Now, there's a lot packed into this slide, and I think I put a lot in here because I'm trying to convince you that this is actually a reasonable thing to do. I'm sort of trying to be persuasive by adding lots of detail. But there's a couple of things that I want you to take away from this. That it's possible to describe how the probability of the dipole state evolves as a function of time, and it can be described by this so-called Kramers-Moyle expansion. This is essentially a Taylor series expansion, and if we were to truncate that Taylor series after the first two terms, we would have a Fokker-Planck equation. This also has a lot of structure and similarity to an advection diffusion equation, where this sort of D1 term would correspond to the velocity. And in fact, in this context, the D1 is often referred to as a drift term. And in the advection diffusion problem, this D2 would correspond to the diffusion. In this problem, it's also called diffusion terms. So even though there's a lot of detail here, the way you actually calculate this is pretty simple. We start with the dipole at some particular state, and we take a small time step forward into the future. If it's a Poisson process, we know that what the probability is that one of these convective events will take place, and that will move us to some new location. And then with 1 minus that probability, we know that we will just simply get ohmic decay. And so you have these two paths, you calculate the expected change in the probability, you end up getting this complicated integral that you can evaluate by expanding into a Taylor series. And this is essentially what that is describing. So there are other quantities that I think are more intuitive that you can probably grasp what's going on here a little bit more clearly. So for example, the drift term, that first term in the probability distribution, can be represented as the gradient of the scalar, this potential. And so what you can see is that this looks like a double potential well. Most of the time, the solution is kicking around one of these, sort of roughly -5 or +5 in these units. But occasionally, random fluctuations are going to be able to move the solution up and over the barrier between, and then we will move down into the other, and we will end up getting a reversal. It's also possible with that equation that I showed in the previous slide to come up with a description of the steady state probability distribution. What would we expect as a histogram if we ran this realization for a very long time? And you can see that most of the time we're either in one polarity or the other, but there's a small fraction of the time when we're actually in between, when we're actually going through from one state to the other and actually undergoing a reversal. Okay, so what I want to do now is I want to actually apply this model to some very specific aspect of the geological record. And one of the really unique things, or interesting things at least, about this geological record is that there's some asymmetry in the way in which the dipole evolves. So here's that PAD-M 2M record. We have the reversal, the last one between the Matayama and the Bruns, which happened at about 0.78 million years ago. But after the reversal, and we sort of reestablished a sort of an average state, what you'll notice is that the declines in the magnetic field, the dipole strength, tend to be a little bit slower than the increases, particularly if you average over these shorter period fluctuations. So there's a positive skewness in the trends of the dipole that is coming from these geological records. The positive trends tend to be larger, and they tend to be less frequent. And so the question for us to address here now is to ask, what does this tell us about the process that's going on inside the core that's generating these magnetic field in the first instance? Can we learn something about that? Okay, so here's the strategy for the approach. We're going to have our record, and we're going to sort of take some window of time. Here in this particular example, it's 8,000 years. And we're going to calculate a least squares fit to the dipole moment over that interval. And then we're going to move to the next 8,000 years, say 8 to 16,000 years. Again, take a least squares fit, get the trend, and repeat this for the entire sequence of data. So if we do that for the paleomagnetic model, we can calculate the skewness, which is really just the third moment relative to the mean, normalized by the second moment with the appropriate powers to make this non-dimensional. And if we analyze that geological record, what we find is the skewness has a maximum of about 0.5 at a time window of about 20,000 years. So if we were to come back to this record, we tend not to see as much skewness on these very short time scales, but on time scales of, say, 20,000 years, 30,000 years, we're starting to see this very strong skewness. So the question is, can we use the stochastic models that I've just described to try to understand what this is telling us? And the answer is we can. So what I'm going to do this is I'm going to let the trend be approximated by just a simple first order difference, essentially. So I'll take the dipole moment at some time plus the window, and then subtract the dipole moment at that earlier time, and then just simply divide by the window that I've used. So this turns out to be a lot simpler than doing the least squares fit, but it's actually remarkable how good this approximation actually works. We can use the probability distribution that I described earlier. It's not obvious, but you can take my word for it that we're able to do this, and we're actually able to make an estimate of the expected value of the trend squared. And it depends on that second, that term, the diffusion term, evaluated at the average and then divided by the window that we've used to calculate that particular trend. And then the third moment of the trends depends on the third component, the one that we added that's sort of above and beyond sort of the standard Fokker-Planck model, and we can make a prediction for what that is. And so if we put these two pieces of information together and make an estimate of the skewness, our expectation is the skewness should depend in the following way on those parameters that are describing our stochastic differential equation. So all that we have to do now is ask the question, what do we have to do to the model to make sure that when we calculate the D3, the skewness term, and calculate the diffusion term, the D2 term, that we actually get the skewness that's compatible with the geological record. And this was a real surprise when we first did this. The paleomagnetic requires that the recurrence time of those convective fluctuations is 3,000 years. And this is extraordinary. It's extraordinary because it's so long, I would say. The conventional view or the thought about how this process works, going back to really classic work of Gene Parker in the mid-1950s, what it was related to these helical flows. The flows were rising, they were twisting because of the rotational effects, and you were taking loops of magnetic field and lifting them and twisting them and producing these loops that are shown in this schematic diagram. And Parker showed that if this was happening all over the core, it would be possible to actually contribute to and generate the dipole field against the persistent losses due to finite electrical conductivity. But the thing that you'll recognize is that the definition of the dipole moment that I gave you earlier simply depends on averaging the magnetic field over the volume. And I think what you can appreciate is that when I produce a loop of fluid like this, that the upward going branch and the downward going branch are going to have a significant amount of cancellation. And so the point is that this is the conventional view of how it works, but it's not a very efficient process. And so given that it's not very efficient, you would expect that this would have to be happening all of the time to sort of maintain the dipole field. We'd expect the recurrence time to be, hundreds of years, tens of years, maybe years, thousands of these convective elements going on in the core. It's surprising then that what came out of this study using the paleomagnetic data was the recurrence time for these convective events was 3,000 years. So one of the ways that we can think about explaining this is to reimagine a little bit the mechanism that actually generates the magnetic field. Let's imagine, just as a hypothetical argument, that we produce a loop of field, just as Parker suggested. But let's also suppose that I could take one of those branches, let's say the upward going branch, and I could have an additional system of flows that sweeps that upward going branch in toward the center of the core. And I have another bit of flow that actually takes the downward going branches and pushes it out toward the outer edge of the core and ultimately expels that branch. Process called flux expulsion, pushes that limb out of the core. So I will only be left with one sign. And now suddenly that would reduce the cancellation and potentially give a much stronger contribution to the magnetic field. So one of the hypotheses is that what we're seeing with this 3,000 years isn't the time scale for these convective eddies to actually take place, but rather it's the time scale for these flux expulsion events to essentially get rid of one of those loops and leave only the one strand, which then contributes in a positive way to the dipole field. And there's actually some evidence that this actually happens in our numerical models. It turns out for the numerical models, we're getting a time scale which is still pretty long, maybe 100 years, maybe 200 years, but there's some suggestion that this flux expulsion procedure is actually taking place. So here's a numerical model. It was run with an Ekman number of 5 times 10 to the minus 5, so it's not exactly realistic. And what I'm showing you in the colors is the vertical vorticity. So connecting back to one of the earlier figures, instead of getting columns with one sort of circulation or the other sort of circulation, what I'm actually getting in the model are more like sheets. And I have circulation in and out along one sheet, and I have circulation in and out around the other sheet to give me the vorticity that this image is showing. But I also have upwelling and downwelling, which are producing those loops. The thing about this particular structure is that the sheet-like nature means that it's very possible to take these different oriented filaments of magnetic field and export one toward the center of the core and to export the other one to the outer part of the core and ultimately expel it from the core. And so if we were to now look at the corresponding vertical magnetic field that's associated with that exact same simulation, what you see is all of the positive magnetic field in orange colors being collected toward the center, and the opposite colored orientations being pushed out, sort of the vestiges of those fields being pushed out and ultimately expelled from the core. So there is some evidence to suggest that the standard mechanism of just lifting and twisting fields isn't perhaps the whole story. The paleomagnetic observations are telling us that some element of separating and separating these fields and expelling one might actually be the mechanism that is underway in the actual core to produce our dipole field. The question you could ask is, well, if we get 100 years for the dynamo models and we get 1,000 years essentially for the paleomagnetic record, how do we make sense of that? And I think the answer is the radial flows in our numerical models are probably not sufficiently realistic. This is the plot of the solution that I showed. It's an Ekman number of 5 times 10 to the minus 5. These are radial motions, so the red motions are basically going toward the outer boundary, the blue ones are coming in toward, and these are the flows that are doing the export along these sheets that are taking these magnetic field lines and either expelling them or collecting them toward the interior. And because these flows are so well organized, I think the process of doing this flux expulsion is very efficient. I think with a more realistic calculation, like this one at an Ekman number of 10 to the minus 7, the pathways are not so clear. The ability to sort of produce this flux expulsion procedure might be a little bit more restricted, and as a consequence, perhaps the time scale for these flux expulsion events is perhaps a little bit longer. And so this has been sort of an encouraging result, I would say, but what I've tried to illustrate is that by using numerical models, by developing stochastic descriptions of the parts of the models that we can actually constrain by observations and then make inferences, we can sort of learn new things. And so the way I can see this procedure going forward, the science and research going forward, be to running numerical models at higher resolution, testing to see whether these flux expulsion ideas are actually viable, whether they provide a consistent explanation for the observations. And this sort of process of having an interplay between the math, the physical models, and the observations is essentially the way that this field progresses. And I think with that, I'm actually be happy to take questions.
Thank you very much, Bruce. It was a great talk. I am looking to see if we have any comments. I think some of us are just fascinated by the beautiful models and colors, and
it is spectacular. I did say this image that I showed was probably done on a cluster on our campus with maybe a couple of hundred cores. This one with the Ekman number of 10 to the minus 7 was run on Mira at the time when it was one of the fastest computers in the world, and it was running on 100,000 cores. So I think the prospect of actually getting all the way to Ekman number of 10 to the minus 16 is probably beyond reach. But the hope is that we put these models closer, maybe the things that we care about will stop changing, and they will be sort of asymptotically in the regime that we're hoping for.
Yeah, that was definitely one of my questions, was kind of as you're looking between the mathematics and the observation and lining up your inferences and predictions with what you can observe, kind of which one's moving faster. Are you able to develop the mathematics at the same rate as you're able to look at observations to see how those line up, or are you able to get more observations before the mathematics catches up?
I think unfortunately the task of collecting observations is a really arduous one. And so for me, I think what's been interesting, the stochastic approach has been relatively new, I would say, and it's giving us a framework for looking at the observations and asking questions that we probably wouldn't have asked if we hadn't had the context of the stochastic model as in the first case. So I'll give you another example. The stochastic model gives you a certain perspective about how reversals happen. The field reverses, but the stochastic models also predicts that there's a continuum of behavior that goes all the way from nearly reversal, partial reversal, completely reverses and then jumps back. And we have a nomenclature that describes all of these different events as if these processes and phenomena are distinct, when in fact it's very likely that these are all part of a continuum of behavior, and that the stochastic model provides the perspective to make it clear that these don't require different categories. They are just different possible outcomes of the same underlying process.
That's fascinating. Well, thank you so much for sharing that and for joining us tonight. I'm looking to see if there are any other questions popping up or if not, we will just thank you again. I know in virtual talks, it's hard to sort of give a round of applause, but
Right. Well, I've been delighted to be here, so thanks very much for the invitation.
Thank you so much.